last two lectures, we have seen various models of three-phase voltage regulator. We have seen Y-connected regulator, closed delta connected regulator, and open delta connected regulator. In this particular lecture, we will take few examples so that we will understand this modeling of regulator in better way. Now, let us see one or two examples of your regulator modeling. So, in this case, I have considered this example number 1. Let us say you are having a primary feeder of voltage 11 kV level. However, I am considering single phase feeder. So, voltage of this will be 11 by root 3, which comes around 6.3 kV. So, here what I want to do, I want to at the end of the feeder, I want to keep the voltage to be 6.3 kV, and the range of this voltage level is ranging from say 6.25 to 6.35, and the current carried by this one feeder is say 150 with 0.9 lagging power factor. In that case, your angle will be minus 25 degree, and the impedance of the feeder is given here. So, I want to find out for this particular current, that is 150 amperes, what should be my tap position of this regulator, so that voltage will be maintained at 6.3 in this case. So, I want to find out. So, basic aim of finding solving this equation is to get the tap position of this regulator. This is first objective, and second objective is to get the RC and XC setting of your regulator line drop compensator circuit. So, start with first we will try to get tap position. So, to get tap position, we should know the your PT ratio. So, the potential transformer which is considered for line drop compensator is having say primary voltage, line to neutral voltage is 6300 volts, and secondary voltage of regulator say 120 volt. Then your NPT ratio of potential transformer is 52.5. CT primary current is 200 ampere, CT secondary rating is 5 amperes. Now, first to get the tap position, what I need to calculate, if the regulator tap is on normal tap position, or if the regulator not at all there, how much voltage I am getting at the secondary. Means if this regulator is not here, in that case I should know how much voltage I am getting it here. Then only I will be able to calculate voltage of the tap position of this particular regulator. So, without regulator, let us say voltage at this point is 6.3 kV. Now, because of this current flow, there will be drop across this impedance here. So, the voltage at this point will not be 6.3 kV, it will be 6.3 kV minus whatever drop which is happening across this feeder, I will get this voltage. So, I can just write voltage at LC here will be nothing but voltage VL here minus ZI, which is drop happening across the feeder. So, if you do that, VL is known 6 with reference angle 0 I am considering, and then this impedance drop Z multiplied by I will get voltage VLC at the end. So, you can see that when regulator is not there or regulator is on normal tap position, I am getting lesser voltage at this end. However, I want to regulate this voltage to say 6.3 kV. So, what I can do then, I can calculate how much voltage I am getting inside the compensator circuit. So, as I explained you, compensator circuit, line drop compensator basically used to get voltage drop proportional to voltage drop actually happening across your feeder. So, voltage drop inside your line drop compensator circuit will be nothing but this voltage divided by your PT ratio. So, if you this voltage divided by PT ratio, I will get your voltage proportional to your LC. Now, based on this voltage I can get the tap position. So, set position of the regulator compensator circuit is say 120 volts, but however across that voltage relay I am getting 115.37 volts. So, this is actually I am taking magnitude of this quantity. So, 120 minus this divided by 0.75. 0.75 is actually if your per unit value 0.00625, it is per unit. Now, for if you calculate this for 120 volt base, it comes out to be 0.75 volt. So, this is per unit, and for if you calculate for 120 volt base, it comes 0.75 volt. It is basically 0.00625 multiplied by base value, this is 120 volt, will give me 0.75 volt. So, this gives me one tap position is particularly inside compensate this line drop compensator corresponding to 0.75 volt. So, if there is difference of 0.75 volt, the regulator will change by one position. So, by how many position regulator will change, that will be calculated by how much voltage difference we are getting divided by per tap position we are getting 0.75 volt change. So, this will give me how many tap position I should move to control the voltage at the line end. So, it is telling me I should get 6.17. However, tap positions are integer quantities. The tap will be set to nearest integer value, which is basically 6. So, tap will be set at 6 value. So, once you get this 6, I can calculate your transformation ratio or your A parameter, which is basically 1 minus, we have seen that it is 1 minus 0.00625 into your tap position. So, here we need to raise the voltage because voltage is lower here. So, we need for raising, as I told you, you need to use minus sign here. So, basically you will get this your A parameter, which is basically AR, is this one. So, in that case new voltage at secondary side of the regulator means at this point. So, at this point earlier voltage without regulator or in regulator normal position we are getting 6.3 kV, but when we shifted this tap to taps number 6, this voltage at this position has raised to value of 6.545 kV. So, once this voltage has raised here, even though some drop happened into this feeder also, you will get required voltage here. Let us see, are we getting this required voltage? Okay, so new voltage which you have got is 6.45, how much it is? 6.545. So, 545 kV here, and then we need to subtract this drop from this voltage. So, new voltage at this end. So, new voltage here minus drop which is happening which is Z multiplied by here I am keeping the current constant. So, load which is connected here deliberately I am considering it is as a constant current load. So, in that case you can see that new voltage after changing the tap position, it is 6.3 kV. So, it is within the range of whatever range we have considered. So, whatever tap position we have chosen, it is correct tap position. Then as I told you, second objective of this example was to calculate impedance settings of your compensator. So, we have derived the formula itself. So, it is actually Z multiplied by CT primary divided by N ratio of P potential transformer multiplied by CT secondary current. So, this impedance of the line is given, and these are the various ratios. This is 200 CT primary, NPT is 52.5 and CT is 5 ampere. So, if you do that, I will get settings of your compensator circuit. So, in this example we have seen that how we can calculate tap position based on voltages at the feeder end, and then we have seen how to get the compensator circuit settings. Let us see one more example. In this case I have considered 3-phase primary feeder. let's say it is 11 kV primary feeder. So all the 3 phases are there. So we are having, and it is open delta connected, means system is basically delta connected system I am considering. So phase to phase voltage or line to line voltage is VAB is 11 kV, and they are actually 120 degree shifted. So basically voltage at this position, actually these 3 voltages with 120 degree exact 120 degree phase shift, because they are actually source voltages and we need to keep them constant at 11 kV. Now depending upon the tap position, the voltage here will vary, and depending upon load currents, the voltage at this bus they will vary, and the drop across all the 3 phases they will be different. And many times what happens, these 3 phase feeders will be having 3 by 3 matrix of impedances. So while calculating the settings of your regulator, which basically need the impedances of 3 feeders. However, here we are having 3 phase matrix. So in case of 3 phase, what we can do to calculate the settings of your regulator, we need to do load flow studies first without regulator. So without regulator, calculate the voltages at this feeder end by keeping these voltages Vs at this end. So if you do the load flow study, in this case it is simple one. What you have to do is Vs minus whatever drop which is happening in this feeder because of these 3 currents in 3 different currents in 3 different phases, IA and IB and IC. You will get the voltages at secondary side. So these are basically voltages at this secondary side, and from this I can get the settings. In this case, these voltages first I need to convert on 120 base. So to convert these voltages into 120 base, what you can do, your PT ratio is 11 kV by 120 volts, which comes around 91.67. So if you divide this quantity by 91.67, I will get these 3 quantities. So this is on 11 kV base, and these are the voltages which are based on 120 volts. So just I have changed the base of these 3 quantities here. Now let us calculate equivalent impedances. Since I am considering open delta here, to calculate equivalent AB and CB, because if you see these delta connected regulators, they will be something like this. You are having these 2 regulators which are basically placed like this, and this is your A phase, this is your B phase, and this is your C phase which is coming out. We have seen that, and there this is basically going to capital A phase, this is going to capital B phase, and this is going to capital C phase. Now if the load is connected here, so this is your load, and then there are transmission line impedances, and then say loads are connected here. Now since there are only 2 regulators, we need 2 settings only, and to get those 2 settings we need to know equivalent impedances of these 3 phases. So we need only 2 equivalent impedances, and based on those 2 equivalent impedances we can get the compensator setting for these 2 regulators. To get the compensator setting of this regulator, so Z equivalent will be equal to, in this case this voltage we can say it is VAB, and this voltage, so this I am calling VAB, and this voltage at the load end I am calling VLAB. So VAB minus VLAB divided by your current, this current is IA, which will give me one setting. So this setting is for ZAB. Similarly, I will get another setting Z equivalent for regulator which is connected between C and B. so it is actually between C and B, will be equal to VCB minus VLCB. Basically CB is nothing but this voltage here, VCB, this voltage here, VLCB I am calling. So this voltage minus this voltage divided by your this IC current will give me another setting. So based on this setting, I will set my regulator between A and C, and based on this impedance I will set my another regulator which is between C and B. So that is why I am doing it here. So this equation you remember VAB, because VAB already we know. So this is VAB, and VL load center voltages VA, this we know. So this voltage minus this voltage divided by IA current will give me Z equivalent AB. Similarly VCB means negative of this voltage minus this voltage minus negative of this voltage minus negative of this voltage divided by your IC current will give me second. So basically okay, so I got these two equivalent settings. So this I got, as I told you, this I got VSAB minus VLCAB divided by your current IA. So IA current, these three quantities are known, and this quantity I got minus VSBC plus VLCBC divided by your current IC here. So these two quantities I got by doing this operation, and as we have seen that settings are obtained by, it will be Z equivalent into AB multiplied by your CTP divided by NPT multiplied by your CTS. So all these things are, I just explained in last slide, it is given. So all these quantities are given here, and we can calculate ZCAB. So these are nothing but RC in AB circuit, and this is XC in AB circuit. So these are the settings of regulators in AB phase, and this is RC in CB and XC in CB circuit. So these are the settings of the regulator in CB circuit. And once you get that, I can get the voltage across the relay, because we have seen that in line drop compensator circuit it is basically something like this. You are connecting this impedance here, and then you are having this 1:1 transformer, and here we are having input from potential transformer, and here voltage relay we are putting. So this is actually 1:1 transformer. So what we can do, this voltage plus this voltage both can be calculated, because this voltage is nothing but whatever voltage we are getting on the secondary side of the transformer. Here we are calculating, first we are calculating to get this tap setting, we are calculating without considering the regulator or regulator on normal tap position. So that is why voltages VL will also be equal to these voltages, and the voltages here it will be 120 volts. So this voltage will be 120 volt, and then based on this settings of two regulators we already calculated. So this, as I told you, this gives me RC and XC. So this RC and XC for AB phase, and this is RC and XC for CB phase regulator. So and the current is also known. So we know the current, we know these settings here. I can get the voltage drop here, because currents are also given. So when I am considering current in phase A, so I can easily calculate how much drop which is happening across this feeder, this compensator circuit. Same drop will come here. So 120 minus that drop will give me voltage across the voltage across this voltage relay coil. So, in this case in AB phase regulator I am getting this voltage across the relay, and for CB phase by considering these are RC and XC values, I am getting voltage across the CB relay, which is basically this one. And using this we can get the settings of tap settings of this one. Tap settings we have seen that we are getting 120 minus 114.62 divided by your 0.75 will give me tap setting of relay between voltage regulator between AB phases, and here a 120 minus 116.6 divided by 0.75 if you do, I will get tap setting for regulator which is placed between C and P. So, these values if you calculate, so here I am getting 7.17 and here I am getting 4.52. So, these are basically tap settings I am getting, and as I told you taps should be integer values. So, I am choosing nearest integer value. So, the regulator between AB phase your tap setting should be 7 plus 7 because we want to increase the voltage, and here we are getting for second 4.5. So, nearest tap position either we can go for 4 or 5, but in this case since it is just more than 4.5 we can choose tap position 5 nearest integer value. So, you can see that for open delta connected regulator how we can calculate your tap position. So, how we are calculating? First, assuming that your regulator is at normal tap position or regulator is not at all there, we are getting voltages at here and then corresponding voltages inside the compensator circuit, and by knowing the difference or voltage across the your voltage relay coil we are deciding your tap position. So, in the summary of today's lecture, to understand the regulator better, in this particular lecture we have taken two examples. One is on single phase voltage regulator where we have calculated the settings of single phase voltage regulator, so that voltage at the feeder end will get at required bandwidth. Similarly, we have taken one example of three phase voltage regulator modeling where we have considered regulators which are connected in open delta fashion, and in this case also we have calculated tap positions of those two voltage regulators which control voltage at the feeder end. Next class we will start with load models. Thank you.